Yes, I know, I haven't uploaded in quite a while. Things have been busy behind the scenes, and a lot has happened since my last video. From loosely related tasks, like creating a website for this project, which is not finished yet, but might be live by the time you watch this video, so go and check the link in the description. To designing the heatbed and extruder assemblies, with a couple of non-traditional features. I was, in fact, expecting this video to take quite a while due to the goals I had in mind. Firstly, I aim to integrate a 3D Pro into the extruder. Keep watching to see how this super odd assembly achieves that. Secondly, I wanted to create a heatbed that could rotate indefinitely in any direction, yet still be capable of heating up and measuring temperature. I have successfully achieved that too. Fortunately, I've received some timely help. PCBWay reached out to sponsor this video, and their offer couldn't have come at a better time. I was grappling with the challenges of designing an efficient mechanism to transfer voltage from the fixed parts to those that need to rotate indefinitely. I will go deeper into my struggles with alternative ideas later, but let's just say that the cleverly designed PCB solved the problem quicker and better than I expected. Additionally, I needed a small heatbed, and heatbeds are also typically constructed using PCBs. It is important to note that many of the things I will be showing in this video were completely new to me when I started. I just had some ideas and concepts in my mind, but nothing concrete. Designing a PCB and sending it for professional production was also a first for me. The anticipation of seeing the finished boards was quite high, and I was just a bit worried about messing them up. After all, in everything I create, I tend to make mistakes and often end up printing the same part more than once. This time I put extra effort here to avoid any silly mistake and the need for a redo. In a way, I was overstressing for nothing. The service is super quick and wouldn't have been a huge setback to wait just some more days. But luckily, they all work as I wanted. I will go through the process of designing and uploading the PCBs for manufacturing later. Like always, I want to be clear about the current status of this project. It's still in the prototype stage. When it's ready, I will post it on the website I am creating as an open source, and by then it will have a proper name. For now, I simply refer to it as 5-axis 3D printer, which admittedly sounds a bit blunt. Naming things isn't really my strong suit, so if you have any creative idea for what we should call this frame, please drop a comment. I would love to hear your suggestions. So let's get started. I will begin by outlining my overarching goal for this iteration. This is important because without understanding this, the decisions and designs I made won't make any sense. Okay, let's start from the very beginning. This printer was missing the two most crucial components, the heatbed and the hot end. Coincidentally, those are the exact parts where I wanted to experiment with some new ideas. So let's dive into the requirements. 1. Extruder functionality. The extruder should be fully operational, obviously. Second, integrated sensing. The extruder tip itself should act as a sensor for the bed. I am aiming to avoid using an offset probe. Third, 3D probing with extruder tip. The extruder tip should function as a 3D touch probe, similar to the probes used in CNC machines for detecting holes, borders, corners, etc. in the material. Fourth, heatbed functionality. The heatbed temperature should be controllable. Fifth, unlimited rotation of the heatbed. The heatbed should be capable of rotating indefinitely while still being heated. Sixth, the heatbed should have 2 holes at known places for calibration. This design will enable the use of the touch probe mechanism to locate one hole and then the other. I should be able to make an algorithm that uses some mathematics to leverage the probed holes for fine-tuning the bed position. I haven't worked on any of the coding just yet. The focus of this video is in the hardware aspect. Next one will be about the code changes. There are 4.8K forks of Clipper, so I don't think it's unlikely that someone did something similar before. But I didn't find anything yet. In any case, the goal is to learn more of Clipper's codebase, so I'm happy to just try to program that by myself. Now you can see the reasoning behind my desire to use the extruder tip for probing in 3D, specifically targeting one hole and then the other. This method is crucial for achieving the precision and functionality I want on this printer while still being built with imprecise materials like printed plastic. With those objectives in mind, let's begin with the heatbed. It's arguably the most aesthetically pleasing part of this iteration, specifically when compared to the extruder, which currently has a 3D probe somewhat awkwardly attached to it. As I mentioned in a previous video, my idea for the heatbed to work at temperature while also allowing the entire axis to rotate freely required me to design something similar to a mechanism used in gimbals. I realized that 4 wires were necessary, 1 positive, 1 ground, and 2 for the thermistor signal. My design incorporates a truss bearing already, which is metallic and therefore conductive, and I can leverage it as one of the 4 lines I need. This meant I needed to add 3 more channels somehow. Initially I thought, just get different sizes of truss bearings, nest them into each other, and done. So I bought myself some, paying little attention to the sizes. I just wanted to get my hands into them to see if I could come up with something, but realistically finding the right truss bearing isn't easy or cheap. They are also quite heavy and big, and I want to minimize the weight of the entire axis. So nested truss bearings were off the table. Then I thought about those little metal carbon brushes used in motors of angle grinders. That could work, but I need to buy some and wait for delivery. What I did have, however, were small metal balls I had acquired at some point. I theorized they may do the trick if I managed to work around the lack of precision of plastic parts. Those 3mm wide balls seem massive in the workspace of Fusion 360 on a big screen, but in reality they are really tiny. And that leaves little clearance for plastic parts, which tend to be imprecise. Although I had little faith on this approach, I decided to give it a try. Here is what I came up with. 2 identical small boards, which can be used in a mirror fashion. I had PCBWay produce 10 of them for me, though I only needed 2. They are designed to face each other, and in between I will have to carefully position many small metal balls, ensuring they stay in place. The tiny plastic rings I created to hold the balls also had super tiny pins, intended to thread through the board. In practice, those holes were just 2mm wide. It still amazes me how well this worked. I was fully prepared for another round of failures before reaching this point. I did though have a moment of panic when I first tested the setup because the power connector wasn't transmitting power effectively. Then I realized what the issue was. I had 2 different sizes of metal balls. Some were 3mm wide, some others 275. When I switched to using only the 3mm balls, the signal breakage disappeared. It's worth noting that I did have other ideas in mind before PCBWay reached out, but none as easy to implement and precise. One idea was to 3D print the boards and use copper foil tape, but that turned out to be a complete hassle and didn't even adhere properly. I could have also used some tiny spring or a little metallic brush, etc. But I'm happy I had this option available. I think it saved me some days of struggle. Another feasible option was to use this little thing I have here, called slip ring. My concern about it is that the cables are too thin and may not support the amps I need. Additionally, this piece looks a bit brittle. I will surely crash the nozzle in the bed a few times, so this will be under pressure and it may break. So let's better work with parts that we can easily reprint and rebuild. Now, regarding the design of the PCB, I used EasyEDA, an online and free tool. I did consider Altium Designer, but it was too expensive and definitely overkill for my needs. EasyEDA was more than sufficient for this project. This was my first time using it, and I picked it up quickly, but I am not in a position to make a tutorial, as I am still very much a noob. Let me summarize the process from nothing to production. Firstly, I wasn't sure where to start. Should I design the boards first and then the plastic parts, or vice versa? I decided to mock them up in Fusion 360, kind of like creating a placeholder. Then exported the sketch of such placeholder and imported it into EasyEDA, where now I have good references as to what size the board should be. What I did then was create a simple circuit with just 2 connectors, switch to PCB design mode, learned how to use the tools at the top to draw traces, fine-tune the traces by editing properties on the right and setting up a proper grid system to suit my needs. Place guides and text on the printed ink layer to identify each prototype. Duplicated some designs a few times to create slightly different variations of the same board. Checked everything in the 3D view to ensure it looked correct. Exported the manufacturer files package. uploaded into PCBWay's site. Afterward, I re-exported from EasyEDA back to Fusion 360, only the DXF file, which is kind of equivalent to a sketch. I found that EasyEDA's feature for exporting 3D models just didn't work reliably. So that DXF file was the only way I now have to bring the board back with all the precise locations of the connectors, which I need to rework plastic parts to leave space for them. Then came the time to place my order with PCBWay. Despite the sponsorship, I proceeded as a normal user. I wanted an authentic experience, so I placed and paid the order myself. After I completed the order, I informed PCBWay and they graciously refunded my payment and upgraded the shipping to a faster option. Now, let's talk about their web interface. It is filled with numerous options, but thankfully each one is well explained in the tooltips, making it easy to understand their functions. If you are ever in doubt, you can always ask what that means to our new ChatGPT friend, while it's still in good terms with us humans. One option that particularly caught my eye was the possibility of printing the board in aluminum. It was a bit more pricey, so I decided to try it on just one of the boards. The rest were standard PCBs in different colors. Interestingly, the price varies for some of them. Purple and matte black cost more, but they are also my favorites. In the future, I may splurge on those once I am more confident in my PCB design skills. It is worth experimenting with all the parameters. Sometimes you can get better features for a lower price. For instance, a double-sided board was cheaper than a single-sided one. A win-win situation for me since I could test two prototypes at once. I also copied one tooltip help section from the site, the one that explains thickness of copper per layer, and I fed it straight into ChatGPT alongside other parameters like trace length and width, and then asked it to estimate the resistance. Admittedly, I may have cut a corner I shouldn't have in there. I actually did check the reasoning and logic behind the calculations, but not as thoroughly as I should have. So the resulting resistance is somewhat off the expected values. The end result was stunning nonetheless, and the actual resistance is something I can live with. I bet you have never seen someone so thrilled over something that simple. At the end of the day, those boards don't even have a single component other than connectors, but what I appreciate them for is for what they represent. If you think so, nowadays we can just design pretty much anything in the computer and have it manufactured and delivered some days later for relatively cheap and with excellent quality. I am just really appreciative of the options we have and the current state of technology. While assembling, I learned a crucial lesson. Soldering on stainless steel is not effective. It may seem to work initially, but soon you realize that the parts are held together more by flux and hope than anything else. Fortunately, there is a solution, using a spot welder. I bought one about a year ago. The spot welder allows for the use of nickel strips, which then can be soldered into the board. The process involved a little bit of trial and error. I finally managed to correctly position the washer of the truss bearing in the center of one of the boards. The lower one aligns with the PCB. Aligning the upper one was more challenging, requiring it to be slightly off-center. It took several attempts to get it right, but here it is. During the testing phase, I initially went overboard on testing with the oscilloscope and the Flipper Zero. I have to admit that was a silly overkill. I just wanted it to look cool in the video. But a more simplified testing approach proved to be more effective. Now, only time will tell if this assembly is the ultimate solution to the problem. I'll need to use it extensively to assess the wear and tear on both the boards and the little balls. The significant amount of amps passing through one of the lines is also a factor to keep an eye on. We will see if anything ends up melting down. Don't worry, I won't leave this unattended until I am sure it's safe. Next, let's discuss the heatbed. I opted for a small surface instead of a large heatbed. I am not entirely sure yet how practical this will be for real-world applications, but we are still ways off from that stage. My goal here was to create something that doesn't restrict the movement of the A and C axis too much. That will speed up the testing phase. The process of creating the boards was similar to what I described before. This is when I used the resistance values calculated with ChatGPT. Also, it's the same consideration than before during the design phase. The lines appear quite large on the screen. However, in reality, we are dealing with very thin lines of fractions of millimeters. During design, I wrote the theoretical resistance and the expected amperage for each board at a given voltage on the board's ink layer. After receiving them, I tested the actual resistance and compiled the results into a graph. There are some discrepancies between the theoretical and actual resistances. I am surely missing something here. Maybe there is a reason for the calculation to not be as precise. Some real-life factors may affect it and I am not even aware, or maybe the calculation I instructed ChatGPT to do was not good enough. Feel free to drop a comment if you know better. In total, there are 7 prototypes. One is made of aluminum and is single-sided, while the rest are standard two-sided PCBs, allowing me to experiment with different parameters on each side. Now that I have seen all of them functioning, I am leaning towards the aluminum one, admittedly just because it's made of aluminum. The heatbed should work well with any of the other PCBs, so I just chose the one I like better. But for now, let me show you this video of the boards heating up. During assembly, I forgot to add the thermistor, but that is an easy fix with some tape, kept on tape, to be precise, which is heat resistance. Now let's talk about the extruder. First off, I decided to use my old flexion extruder. I am aware that there may be lighter options available nowadays, but it has worked well for me and I have no good excuse to buy new stuff just yet. I also used a mosquito hot end, which I had bought some time ago but never used. I designed an interface to connect the flexion with the mosquito, along with some mounts for the fans. After that, I began working on the more intriguing part of the setup. Just like before, I draw inspiration from the things around me. One thing I have observed is that CNC machines have to be able to detect edges, corners, holes, and the like. They can do this thanks to a specialized tool known as a 3D touch probe, which is capable of detecting deflections in any direction, X, Y, or Z. Now, CNC machines benefit from a fantastic feature called tool changers. The 3D printing community is also experimenting with tool changers, and they look incredible. I definitely plan to integrate something similar into my setup one good day, but that day isn't here yet. For the time being, I have developed a mechanism where I use a single tool, a direct extruder plus hot end combined with a 3D probe. I can already imagine what you're thinking. This is too big, heavy, complex, lengthy, and convoluted. Not good at all, and I have to agree. Generally, extruders are supposed to be lightweight and streamlined. This design, in contrast, might limit the speed at which the tool can move without creating artifacts. The reason for this is the necessary looseness to facilitate probing, which may be triggered by rapid acceleration. To address this, I could either keep adding more parts, like a tiny servo to block all the movement, or refine the current design. Either case, not ideal, but I am keen to give it a try. This approach might be questionable, but I am not in any rush. And if it doesn't work out, I will simply rework this and try again. Either way, I am sure to learn a great deal in the process, which is a win in my book no matter how you look at it. Let me show you this freak in action. Do you like it? Probably not. It's not so good looking, but check out this feature. When I apply pressure on Z axis, it triggers. And that also happens with pressure in X and Y. How does it work? Initially, I considered using a pressure sensor, but I eventually took a different route. I examined this probe I had bought for my desktop CNC, and I also studied a model I found online to understand the internal mechanics. Interestingly, the little metal balls and the spot welder came in handy here as well. Looking at the cross-section, the mechanism essentially rests on 3 points, which are metal balls. Those balls, in contact with 2 metal rods, act as a switch. When the surface is held atop those 3 spots by spring pressure, it keeps the switches closed. But any pressure applied at any angle will cause one of the pivot points to lose contact, thus opening the switch. Now, with these 3 switches instead of 1, you could use simple integrated circuits with AND gates to merge a signal into one single output. However, I don't have those ICs at hand, nor I have ever used one. Remember, my background is software? Well, for me, it's simpler to use an Arduino with some basic logic. It might seem like overkill, but it's cheap, lightweight, and gets the job done. In designing this assembly, I initially tried positioning the probe vertically, but that was a complete failure. I had to go back to the drawing board and redesign the entire part to make it work. During assembly, I encountered the issue of tight tolerances again. I was dealing with very thin metal rods, and same as before, I ended up using nickel tufts and the spot welder to make the connections. Take a look at this close-up of the weld. I really like close-up shots like this, but I think this particular one was a bit too close. The circuit for this assembly is quite straightforward, and so is the logic behind it. I am working on a website for this project to make all the resources easily accessible. For the time being, I will flash a circuit diagram on the screen. As for the Arduino code, I have uploaded it to a GitHub gist, and you can find the link in the video description. So at this stage, the entire printer is designed, constructed, wired, and configured. However, there is still some programming work to be done. If I want to utilize all the features I've designed, like locating those holes, leveling the bed, and actually printing, some coding is definitely in order. But before I wrap up, I want to address a common point brought up in the comments. The apparent futility of building a 5-axis 3D printer when there are no slicers available that can fully utilize the extra axis. I just want to say I am fully aware of this, and I do agree that the slicer is the most difficult part of all of this, probably by far. But consider this, if I were programming a 5-axis slicer instead, couldn't the argument be that it's pointless without a 5-axis printer? We have to start somewhere, right? I am confident that soon enough I will manage to print in 5-axis. G-code isn't black magic either, it's actually quite straightforward to write manually. The real challenge lies in converting a 3D model into a 5-axis slice program that can be executed. No, that is the real ultimate goal. But we don't even need to go that far to see this working and making cool stuff. There is a wealth of possibilities and ideas in this space. I am not the first to attempt a 5-axis printer. In fact, check the description. I will link to a channel of a creator who built a 5-axis 3D printer with a different approach than mine. He commented on my last video, and I discovered he even modified Clipper's code to include A, B, and C axes, not just A and B like I did. A big shout out to him. His modifications and mine are similar, but his code is more polished at the moment. I invite you to take a look around his channel and GitHub account. In my next video, I will take a look at his code. I think there is a part I can borrow. He mentioned that I could branch off his fork too, so I might explore that option if it seems fitting. Through his work, I also came across another repository, a tool for creating 5-axis G-code using Python scripts, which could be instrumental in demonstrating proof of concept with some unique shapes using 5-axis. With that said, it's time to wrap up this video. I won't promise a quick follow-up this time, as I will be away on a trip for a month. When I return, I will get back to work on the printer. Meanwhile, I will finish a website while I am overseas, so keep an eye out for that. If you want to stay updated on this journey, feel free to subscribe and leave a like if you enjoy the content. Thanks a lot for watching.